Now started. Now in today's lesson, we are going to be looking at electrostatics. When you hear the word electrostatics, you want to study charges at rest. Electron in that word represents electric charge. An electric charge in physics can be denoted as Q. Why statics means that something has rest. So we're looking at the study of charges at rest. Now, according to this scientist, his name is what? Benjamin Franklin. Yeah. According to Benjamin Franklin, he proposed that we have two types of charges. And those two types of charges are what? We have two types of charges by Benjamin Franklin. We have two types of charges. Two types of charges. Altogether.
Yes, sir.
What are these types of charges? We have what? Positive charge. We have the positive charge. And you see positive there. Also, we have what? Negative charge. Just like we have in an atom, protons are positive, electrons are negative, while neutrons are neutral. Okay, so we have two types of charges, the positive charge and we have the negative charge. Are we together?
Yes, sir.
So how do we even verify that we have two types of charges? Let's quickly look at this simple experiment to verify that we have two types of charges. Let's look at this simple experiment. So let me say that, let me quickly sketch a simple diagram. Let me sketch this simple diagram. Now we have something like this in this diagram, and we have something like this in this diagram. I'm coming. We have something like this in this diagram. I'm coming. Let me draw it way. Let me say I have something like this that is styled this way. Good. So we have something like this that is styled this way. Exactly. So take note that this rod that you are seeing here, this is a rubber rod. This is the rubber rod, a rubber rod. And take note that what this rubber rod has been rubbed with four. Has been what?
Rubbed with four. Rubbed with four.
Exactly. F-U-R. Has been rubbed with four. Now, also in this diagram again, we have something like this. We have this. Let me see what we have here. What you are seeing here is a what? Is a glass rod. And this glass rod that you have here, it has been what? It has been rubbed. This is a glass rod that has been what? That has been rubbed on silk. That has been rubbed on silk. Good. So this is what we have. Now, let me quickly sketch what we have here on this other side also. Let me quickly sketch what we have here on this side. So we have this rod, a rubber rod, like this. So this same rod here, exactly. Okay. Also, we have the same thing. So this rubber rod that has been rubbed with four. Now, if you take this glass rod that has been rubbed on silk closer to this rubber rod that has been rubbed with four, what do you observe? You observe a force of attraction between them. You observe what? A force of what? A force of attraction between them. You observe that these two will be attracted to each other. You have a force of attraction between them. Exactly. You observe a force of attraction between them. That is, if you take this rubber rod that has been rubbed with four closer to this glass rod that has been rubbed with what? With silk. If you take them closer to each other, you will observe that what? They are going to what? Come closer to each other. They are going to attract each other. That's the first experiment. Now, secondly, you see this glass rod that you have here. I will take another glass rod, exactly the same glass rod that has been rubbed with the same 4. That is, I'm taking the same glass rod that has been rubbed with 4. I'm coming, let me try to draw it very well. The same glass rod that has been rubbed with 4. You observe that these two will repel each other. These two will what? Will repel each other. This one, there's repulsion here. Why this one, there's what? There's attraction here. Why this one, there's attraction here. Now, pay attention. You see, according to Benjamin Franklin, he proposed that whenever a rubber rod is rubbed on a 4, this rubber rod acquires what we call a positive charge. Acquire what we call what?
Positive charge.
Sorry. Let me take that again. A rubber rod that has been rubbed with 4 acquires what we call a negative charge. A what?
Negative charge.
It means that there is negative charge. There is a net negative charge on. If you see me write negative like this, it does not mean it's only negative charge that is present here, but it means that we have more negative charges than positive charges. Are we together?
Yes.
That is, we are going to have a net negative charge on the rubber rod. Also, if a glass rod is rubbed on silk, this glass rod, we have a net positive charge. Acquires a what? A net positive charge. Are we together?
Yes, sir.
And if you observe what takes place here, attraction. But if you observe here, I'm only having negative charges. And here we have only negative charges there. So what did you observe? Then you are going to see what? A force of repulsion here. Now, this shows that we have two types of charges, positive and negative. And from here, you can easily observe what we call law of electrostatics. What's that law? The law states that what? Unlike charges attract each other, as you can see here. Why what? Like charges what? Repel each other, as you can see here. So let me ask you, if I bring a glass rod rubbed on silk with another glass rod rubbed on silk, what do you observe?
Repulsion.
Repulsion, exactly, because what they are what? They are the same.
Yeah.
Do you understand that?
Yes, sir.
Exactly. Good. So that's that on that. And take note of some facts that were charges. Now you have to take note of some stuff that was notes that I'll be explaining them as I'm writing this for you. That was electric charge. Note that electric charge is always conserved. It's always what?
Conserved.
Yes, it's always conserved. That is, you want to look at conservation of electric charge, just like the way we have conservation of matter, conservation of energy. Now, let us look at what we mean by what? Conservation of what? Electric charge. Now, when an object, pay attention, when an object is rubbed against another object, take note that what? Charge is not created. What did I say?
Charge is not created.
Charge is never created. Charge is not what's created. Like what is happening here, and I told you that what this glass rod has been rubbed with 4. Take note that what this negative charge was never created. Yes. Take note that what charge is not created. When an object is rubbed against another, what happens against another? What happens? Charge is not created. But what happens? How do we get this charge? Take note that when two objects are rubbed against one another, what happens? Charges are being transferred from one object to the other. From what?
One object to the other.
For example, now let me bring this example here. Let's take a look that one. Look at this rod. This is a rubber rod, or I say ebonite rod. And this has been rubbed on silk. Let me say this is silk cloth. Now, this is silk cloth, and this is what? This is a rubber rod. Now, pay attention. This is a rubber what? Rubber rod. Now, pay attention. Now, if I rub the two against each other, let me tell you what I'm saying. If I rub the two against each other, now check. This is the rod. This is the rod. Now check. I'm rubbing these two against each other. Now, how can we explain what is going on here? Take note that what you see the negative charge that appear on this rubber rod, it is never created. What happens when you rub a rubber rod with a silk cloth, what happened? Take note that the rubber rod, I was gonna wait, is it silk or I mean four, please? Not silk, I mean four. Are we together?
Yes, sir.
That is four. This is four. Please take note. So when you rub both of them together, what happens? You observe that what this rubber rod acquires negative charge from the four. That is, negative charges are being transferred from the four to the rubber rod. Take note of that. Negative charges are what are transferred from the what? From the rod, from the four to the what? To the rubber rod. That is why the rubber rod will have more negative charges than positive charge. Then it will what? It will acquire a net negative charge. So what happens is that what electrons, that is, electrons are being transferred from the four to the rubber rod, and that is why acquiring what net negative what negative charge. Are we together?
Yes, sir.
Are we together?
Yes,
Okay.
sir.
On the other hand, let's look at the glass rod now. Look at this glass rod rubbed on silk. How come that the glass rod have positive charge? Now, pay attention that we cannot transfer proton. It's only electron that is being transferred. Are we together?
Yes, sir.
Take note that electrons are the lightest. Please, there's nothing like and the proton will now move. No, no, no. What move
Sir.
is electron. Now, pay attention. If
Sorry,
I
sir.
have if I have something that is having net
I'm
negative
sorry,
charge,
sir. Okay.
can you hear me?
I wanted to say something.
Okay, I can hear you.
Like for this the rubber rod now became has it now has a net positive charge because the glass
Rubber
rod.
rod. The
Yes,
glass rod is having net positive charge. Yes.
so now the rubber rod now has a net negative charge.
Yes.
So I'm not thinking that this glass rod that has a net positive charge is because it lost or
Ele-
electron left it.
Exactly.
So
Yes,
the
correct. Now that
it
was
was no
explain.
longer balanced again.
What
So
do you
it now
say?
has more so the glass rod now has more positive charges than it
Exactly.
had initially because it
Yes.
gave out electrons to the rubber rod.
Exactly. Yes.
Okay.
Yes. Exactly. So that's what I was even about to explain here. So take note that when this glass rod is rubbed with this silk, electrons are transferred from the glass rod to the silk. So if they ask you that if you rub a rubber rod with a four, what charge will you have on the rubber rod and what charge will you have on the four? The rubber rod acquires negative charge, but the four will acquire what? Positive charge. Are we together?
Yes.
Exactly. And then again, if you rub glass rod with silk, the glass rod acquires positive charge and the silk will acquire negative charge. Are we together?
Yes, sir.
Exactly. So take note of that point, very important. And take that what the total charge is conserved. Yes, no charge is created. Yes, there's no creation of charge. The total charge do not change. That's the meaning of this. The total charge is what is conserved. Are we together?
Yes, sir.
Exactly. So that is about this. That's the first one. Now, secondly, is about the discovery of Robert Millikan. About what? The discovery of what? Robert Millikan. Another notes about what? Robert Millikan. You have heard of Robert Millikan before. The person that
Yes.
discovered the charge of an
Yes.
electron using oil
Yes.
drop experiment. Right?
Yes. Yes,
Good.
sir.
Now, take note that he explains that what electric charge. He explained that what electric charge occurs as integral multiples. As integral multiples of this electronic charge E, which is 1.602 times 10 raised to power what? Minus 19 coulomb. Yes. Let me tell you this thing. What's the meaning of this statement? It means that electric charge exists as a discrete packet. What I say? Electric charge Q exists as a what? Discrete packet. discrete. But why not the word discrete data in statistics? What does it mean? Discrete means that it's always whole number and not decimal. That's what it means. Altogether,
Yes, sir.
that is, according to Robert Millikan, we have Q is equal to NE. You can use small letter n or capital letter N, plus or minus NE. Okay, N is an integer. Where N is an integer. Where N is an integer. Altogether.
Yes, sir.
Exactly. So this N, that is the charge on electric charge, can either be, let me say, Q equal to 1E or 2E or 3E or 4E. Just saying that the coefficient will always be an integer. Yes. Now check, is this an integer? 1.6 times 10 is power 2. Is that an integer?
Yes, sir.
Exactly, and that's 162. It will always be an integer. All right, that is for that. Are you following?
Yes, sir.
So you see this, observe what is going on here. When I'm rubbing one object against the other, there will be friction between them. So objects are being charged by friction here. Do you understand? This is what we call charging by friction. Are we together?
Yes, yes.
Exactly. Just like if you comb your hair rigorously, that comb can attract some piece of paper. Exactly. So that shows that charges has been acquired by the comb. So let's go. Charging by induction. Let's look at charging by induction. Charging by induction. Charging by induction. Before I explain charging by induction, in fact, let me first explain something, please. What I want to explain first is charging by conduction or contact. Charging by conduction, or you say contact. All together?
Yes, sir.
Contact. Or you say conduction. Anyway. So I don't want you to understand this main idea. Observe. Let me say that, check. I have a rod like this. Let me say I have a rod like this. And this metal rod is having a net negative charge. Are we together?
Yes, sir.
Good. And I have a neutral sphere standing on an insulating, it is on an insulating stand like this. And I have a metal sphere. Good. So this guy that you are seeing here is neutral, and this was negatively charged metal rod. Now, pay attention. If I bring this negatively charged metallic object close to this neutral sphere, for example, like this, remember, we are looking at charges by contact. It means that these two objects will touch each other. For example, do what I'm saying. They are going to be in touch with each other. They are going to be in touch with each other. They are going to be in touch with each other. Then what happens? Remember, I have some charges here. So since they are in touch with each other, what happens? Electrons are transferred. Electrons are transferred from this negatively charged metallic rod to this neutral sphere. Are we together?
Yes, sir.
Then when we now separate both of them, we will observe that, check, we have some charges. Why some of negative charge have been transferred to this? Then observe, on this metallic, on this sphere, you now be having what? A net negative charge on this sphere. So you can see how we've been able to charge a neutral metallic sphere by touching it with a negatively charged metallic object. So this one is now charged. Are we together?
Yes, sir.
It's charging by contact. From the name, you observe that we charge by bringing a charged object close to a neutral object. Are we together?
Yes, sir.
They will be in touch with each other. But this way, everything will twist. Is it possible for me to charge an object by not bringing them in contact with each other? Is that possible? Then that will lead us to what we call, all together?
Yes, sir.
That will lead us to what we call charging by what? Sorry. Charging by induction. Charging by induction. That's charging by induction. Charging by induction. Charging by induction. Okay. Now, pay attention. This thing, I have different examples to give you. So just pay attention so you will get all the full understanding. All together.
Yes, sir.
Okay, so let me say this is the down level. Observe. Let me say I have a neutral metallic object here. This is an insulating stand. You observe. These are just insulating stand. These are insulating stand. Exactly. Now pay attention. Okay, this is a neutral metallic sphere. This is neutral. Now pay attention that I have a negatively charged object. Then I brought this negatively charged metallic object close to this neutral sphere. But if you observe, are they in contact with each other?
No.
Now pay attention. Don't forget our previous law here, the law of electrostatics, which says that what unlike charges will attract, and like charges will repel. Now, because a negatively charged object is brought close to this sphere, what happens? There'll be a kind of separation of charges, whereby, remember, positive charge will build up on this side. Positive charge will build up on this side, while negative charge will build up on this other side. Why is this thing happening? It's happening because, remember, unlike charges attract each other. So this positive charge will be kind of attracted to this negative charge. Are we together?
Yeah.
Good. Then what do we now do? Yeah, what do we now do? Now, we will now look for a metallic wire, connect it here. If you don't see wire, you can use your hand to touch it. But why are we connecting wire? Pay attention. We'll connect a wire from here down here. You see what I'm doing here? We call it earthing. What do I call it?
Earthing.
Yes, or grounding. That we are connecting this to the ground. Why? So that those negative charge can be transferred to the ground. Are we together?
Yes, sir.
So that those negative charge can be transferred to the ground. Then when they get transferred to the ground and you now separate this, then what happens? We will now be having something like this. You will now be having something like this. This is what we'll be having. This is what we will be having. Sorry, this is what we'll be having. This is what we'll be having. We'll be having something like this. This is the sphere. And the sphere will now be having what? A net positive charge. Are we together?
Yes, sir.
A net positive charge. You can see how we charge this neutral metallic sphere. We charge it positive by what we call induction. You see, the separation of these charges, we call it a name. Let me first explain again from the beginning. This is a neutral sphere. We bring a negatively charged metallic object close to it. Then there's a kind of separation of charge between them. This separation of charge, we call it polarization. You can say this sphere has been polarized. Has been what?
Polarized.
Then what happened? There is a kind of separation of charges. They separated this way because of the fact that unlike charges will always come close to each other. Then how can I get rid of this negative charge? Remember, I can always transfer negative charge. Yes. So I'll connect this to the ground, or I simply use my hand to touch it. Then the negative charge can pass through me to the ground. Then what happens? This negative charge, this electron here, you see, they'll move to the ground and you'll be having a net positive charge. So this is now what? Positively charged. Do you see that?
Yes, sir.
Positively charged. So that's first example by induction. Another example is this. Let
Sorry
me
to
give
say,
you, what is it?
after the attraction between this insulating material and this bar or something. So like it's going to be neutral again now.
No, it won't be neutral. Let me explain it again. When you bring this guy close to it, remember you have hurt this guy already. The electron has moved down already. Then what do? After the electron has moved down, you now take this away. You observe that what you are going to be having, you'll be having more positive charge because negative charge has been, it has been grounded already. It has been taken away.
Yeah.
You get?
Okay. Yes.
Has been taken away. That's the usefulness of this ethnic that you see here. Exactly.
Okay.
Yes.
Okay.
But then look at a kind of another example. Okay, what if you have something like this? What if you have something like this? If you have something like this, whereby um we have these two metallic sphere, you have these two metallic sphere, you have these two metallic sphere, and a negatively charged rod is. You should have asked me why am I using negative. Don't worry, I'll do another example of positive now. Are we together?
Yeah.
Good. Now observe what happens here. Remember, these two are neutral. Then what do you think will happen here? Remember, same principle as this one you have above. If you bring this negatively charged metallic object close to this neutral sphere, what happens? There'll be a kind of separation of charges. You observe, positive charge will build up around this side. But why negative charge will kind of build up around this side altogether?
Yeah.
Don't forget, because of the fact that unlike charge, we always want to attract each other. So you have a kind of, you see that electron will move towards this side because of what? Force of repulsion. Are we together?
Yes, sir.
Good. Then, what do we do after this? Observe. What do you think will happen after this?
Then
If I pay attention, if I separate, hello, are we together?
yeah.
I will still put this guy here, like I'll maintain it the way they are. After you do this, and I kind of separate them, you observe, see what will happen here. This is what will happen. You will see, just manage my diagram. I'll separate them away from each other. So what do you observe? This guy will acquire a net positive charge, while the second guy will acquire a net negative charge. This is another example of charging by what? By induction. What you are using to charge the neutral objects will not come in contact with each other. That's it. Good. Look at another example again. Look at another example again. This is a neutral sphere. And let me now say that, okay, I'm bringing a positive charge sphere close to it. What do you think will happen here? What do you think? There'll still be polarization, right?
Yeah.
Unpolarized. If you observe, the charge that will build up here will be a negative charge.
Yeah.
And the charge that will build up here will surely be a positive charge because of repulsion. Then what happens? I will now hit this guy. Or I simply touch it if you don't have a wire. I will hit this guy. This is what's earthing, or I can say grounding. Anyone? Sorry, grounding. Anyone? Now check. Putting this guy to the ground, what did you observe? Let me ask you, what will happen here? Will positive charge move here, or what do you think will happen? That's the question. I want to see whether you apply what I've taught you. Remember, I told you that we cannot transfer positive charge. So what will happen here? You don't know?
I don't know.
Yes. Take note that what never make the mistake that I've seen. In fact, there are a lot of mistakes that people make that positive charge. No. We don't transfer positive charge. So what happens? Electron will move from the earth into the sphere because the earth is a kind of body that stores charges. So electron is going to move. It's going to move from the ground to this sphere. Then what happens? When you move from this ground to this sphere, you observe that we will not have more negative charge than positive charge. Yes or yes? It makes sense, right?
Yeah.
Exactly. So when we have more negative charge than positive charge, what happens? You observe that this guy will not acquire what?
Innate negative charge.
Exactly. So you can see how I've charged this sphere. Firstly, I first charge it from this side. See, I charge it positive. So here I'm also charging it negative. So I've given you various examples altogether. So that is charging by induction. Do you have any question?
No, sir.
Then let's look at Coulomb's law. Let's look at Coulomb's law. You have done this in secondary school, yes or yes?
Yes.
But this one is now a little bit tougher than it. Because what we don't teach you in secondary school, we teach you here. Because you can't learn that in secondary school. Altogether?
Yes, sir.
Now you see difference between secondary school and university now. So remember that remember that we were explaining that unlike charges attract, like charges repel. Now, what can account for those force of attraction and force of repulsion? In what direction? And everything like that. That one want to study. And you know that Coulomb's law states that the force of attraction or repulsion between two charges is proportional to the product of their charges and inversely proportional to the square of the distance between them. Are we together?
Yes, sir.
Exactly. So let me say that I am having two charges now, for example. I'm coming on. Let me say we are having two charges now, for example. I'm having two charges. Let me say this is positive and this is positive. This is positive, this is positive. Everybody knows that what the force that will be here will be a force of repulsion. The force will be directed away from them. Now, I want to teach you something that confuses many people. Let me call this charge Q1 and let me call this charge Q2. Are we together?
Yes, sir.
And let me now say that, okay, the distance between these two is R. That's what we use in force field. We use the distance to be R. Yes, this distance, if you observe, this distance is R. Like R. Now, pay attention. You see, what do we call, you see, firstly, let me tell you something. These two will repel each other, but how do we write the notation? How do we write the notation? I'm coming to this. How do we write the notation? How do we write the notation? Now, pay attention. If I write something like F21, what does it mean? It means that the force of charge 2 on charge 1, that is what it means. Remember that, you see, this line that we are drawing here is the effect of this charge. Remember that this charge, you kind of push this one away that, hey, don't come close to me. Are we together?
Yeah.
You kind of push it away. Good. So that force of pushing this one away like this is this one that we are drawing here like this. And it means F21. I mean that was the force of charge 2 on charge 1. That one we write as F21. All together.
Yes, sir.
Also, if you look at this line, it's a force of repulsion created by this charge 1. Therefore, I'll write this one as F1. F12, exactly. That was the force of charge Q1 on charge Q2. All together.
Yeah.
Exactly. And this is a force of repulsion. It means that in electricity, we can have in electrostatic, we can have force of attraction and force of repulsion. Now, on the other hand, look at this. This positive and this negative. So what do we have here? Now you will see this charge Q1 and this charge Q2. Now remember, they will attract each other. Now, how do we write the force now? How do you write the force? Now, what do we write here? F what? F21. This F21 means that the force of attraction of 2 on 1. Remember that this force here now, we kind of tell this one that, oh, come close to me. Are we together?
Yeah.
Exactly. So that force is what? F21. So why this force is what? F12. Are we together?
Yes.
So the force have magnitude and direction. So this is what? Attraction. This attraction. Are we together?
Yes, sir.
So now, what is now the statement of Coulomb's law? The statement of Coulomb's law is that what the electric force F is, equal. Remember that it's proportional to the product of their charges and inverse proportional to the square of distance between them. So there's a constant here, which is Coulomb's constant K. Then Q1, magnitude of Q1, magnitude of Q2, all over R squared, distance between them. Are we together?
Yes, sir.
Now, pay attention that what this force that we are calculating here now is the magnitude. Is the what?
Magnitude.
Magnitude, exactly. Is the magnitude. That is, I've never calculated any direction yet. So this is just like the magnitude of the force between them. But I'll still talk about the direction. I'll talk about the direction. The direction you are going to use, remember, force is a vector. So it depends on the system that you are having. You are going to be resolving the forces. But pay attention. Let me just give you a formula. But we are not using the formula to solve at all. What that formula talking about? That formula is a what? The formula is a kind of formula that we call Coulomb's law in vector form. All together.
Yes, sir.
That is, I can say in vector form. Well, although I can use this formula to solve, but it is not easy. All together. All together.
Yeah, yeah.
So let me say F12 is equal to K Q1 Q2 over R squared, then times what? R12. What is this R12 cap? This R12 cap that you are seeing here. This R12 cap, what do we call it? This R12 cap is what? Unit vector. Is the unit vector directed. I will show you in this diagram. Directed from Q1 to Q2. Directed from Q1 to Q2. All together?
Yes, sir.
That is this is it. That's R12. Exactly. That's similarly, if I want to say this exactly. If I want to say F21, this is what R21. All together, and R21 will be something like this. All together.
Yes.
That's what we call. That's the. But we are not using this. I can use this formula to solve, but I won't be using this approach. The approach could be a lot confusing. Now, let us now take for instance that we have about 4 charges in a system. Let's say that assuming there are 4 charges in a system. All together.
Yes, sir.
We have about 4 charges in a system. So, how do we find the next force on, let me say, charge Q1? We have 4 charges in a system. For example, let me say we have 4 charges like Q1, Q2, Q3, and Q4. So how do we find the net force on Q1? What do we see? Check on. We say F1 net is equal to, check on. You see what I'm going to do now? I will add all those forces together in vector form. In what?
Vector form.
Not the scalar, exactly. I add the forces together in vector. That is, I will add, remember, I'm looking for the total net force. Remember, let me say I have 4 students. If I forgot the name of my student. I'll call it Ifoma, Pelumi, Ifeoluwa. Let me see, we are having, what name of that lady with Dada in your class?
Lydia. Lydia.
Okay, let me just say Lydia, exactly. So I want to find the first on Lydia. Let me say I want to find the first on Lydia. So I'll say, okay, the first informer is exacting on Lydia. The first, it can be attraction or repulsion. The first this is exacting on Lydia. The first is exacting on this. So I'll add all of them together in vector. That is the first of chart 2 on 1 plus the first on chart 3 on 1 plus the first of chart 4 on 1. Are we together?
Yes.
So you add the forces together, everything in vector form, then you cannot find the net force. Okay, I think that is clear.
Okay.
Are we together?
Yeah.
Good. So that is on this. So let us look at this question. Let's solve this question together. Are you set?
Yes.
Let me teach you how to apply everything I've been saying since morning. Okay. They said that consider, let me say example. They said consider 3-point charges. Isolated at the corners of a right triangle as shown below. As shown below. So we are giving this information that Q1 is equal to Q3, and both of them are equal to 5.00 microcoulomb. Q2 is equal to minus 2.00 microcoulomb. Altogether?
Yeah.
And we're giving a parameter A to be equal to 0.100 meter. Full stop. They say find the resultant force. This is what we call the resultant force. Yeah, find the resultant force. They say find the resultant force exerted on charge Q3. On charge Q3. Now, before I move on, you see this Coulomb's law, you see this K. This K is called Coulomb's constant, and its value is 8.99 times 10 raised to the power 9 Newton meter square per Coulomb square. And this K, it is equal to 1/4 pi E naught, where this E naught is called permittivity of free space. What do I call it?
Permittivity of free space.
Okay, good. Now, so let me now draw the diagram we have. The diagram we have below here. So this kind of x-axis, this align with the y-axis. So let me write the charges. So we have a charge around here. We have this charge here. We have this charge here. And lastly, we have a charge somewhere around here. Exactly. So this is a positive charge, and this is a negative charge, and this is a positive charge. So this Q1.
I think it must be draw diagram like this.
Is there a must to do what?
To draw it like this.
How do you want to draw it? This is the diagram they are
Ammonia.
referring to. Remember,
Okay,
the question is
diagram.
referring to a diagram.
Okay.
Yes. A kind of broken line. Oh. Yeah. So if you observe that question, we are finding the net charge on Q3. Are we together?
Yes.
So the A in this diagram, this is the A. Let me write that one in red. So this is the A. Sorry, this is the A. So we have the A here. We have A here. This is a right angle triangle. If you use Pythagoras theorem, this one give you root 2A. So that's what we have there. And we have given the magnitude. Okay, so pay attention. How do we now solve this question? So I'll be referring back to this diagram. So take notes. All together. Now, firstly, observe, this is our main target. Q3 is our main target because we want to find the resultant force on this Q3. Now, pay attention. What would be the effect of Q1 on this Q3? Attraction or repulsion?
Q1
Will it be
on
an
Q3.
attractive force or repulsive force? What did I say? What did you say?
Repulsive
Repulsive
force.
because they are both positive force. Exactly. So it means that what the force Q1 on Q3 will be this way. Will be this kind of repulsive force this way. Exactly. So the force will be directed this way. The direction will be like this. So I will write F what? F4, do you know what's going to be? F13. Are we together?
Yeah.
Now, the next question. Since we are looking for the resultant force on Q3, what will be the effect of charge 2 on Q3? Attraction or repulsion?
Attraction.
Attraction. It means that what? This Q2 will put this Q3 closer to itself like this. Exactly. So, this is what I'm going to have. And this will be labeled F what? F23. That's the force of charge 2 on charge 3. Good. So let me quickly draw a broken line like this to show you some things. Pay attention that since this side and this side are equal, then this angle you see here will be 45 degrees. 45 degrees.
So I don't get to, sorry.
Okay, pay attention. This is a right angle triangle. Are we together? You can just say these two sides are equal. A, they are equal. Okay, let me say, how do we get this angle?
Yeah, I understand.
Yes. So theta equal arctan of this and this. So you have arctan of 1 is what? 45 degrees. How together?
Yeah.
Yeah, if two sides are equal in the triangle, just take note of that. Okay. Now we have that 45 degrees. Good. Now, before you now start, so if this place is 45, opposite angle, this place is also 45 degrees. So you use it in resolving this force. Okay.
Okay.
Now let's go. Now, firstly, what do we do? What do we do? Pay attention. Don't forget that from our previous talk, we said that F3 net, remember, this is what they asked us to calculate, the resultant force, F3 net, to be equal to the vector sum of what? Charge 1 on 3 plus the vector sum of what? Charge 2 on 3. Are we together?
Yeah.
So you see this force, before you find them in vector form, go and find the magnitude of this force first. So let's find the magnitude of F13. If you observe, I did not put that vector sign on it. What's the magnitude? K, Q1, Q3 over R squared, right?
Yeah.
So if you observe, what's our K? 8.99 times 10 raised to power 9 times what is Q1? You were given Q1 and Q3 to be equal, and that's 5, right?
Yep.
That's 5 times 10 raised to power minus 6 times 5 times 10 raised to power minus. Why am I putting minus 6? Because of the micro sign that is there. This mu is 10 raised to power minus 6, exactly.
Yep.
So that's what I have. Then all over, what the distance between them?
I think it's 0 points. I'm not sure.
If you observe, what's that between 1 and 3? Check it. Check your table. 1 and 3 is what? Root 2a, right?
Okay.
Right?
Yes.
Root 2a. And my a is what? 0.1. Then
Okay.
all square. So if you do this,
How
you
so
are
that
going
is
to get 11.24 Newton because of time. Because I'm late for prayer. Okay?
okay.
But you can verify it yourself. Also, you'll find F23 in scalar in the magnitude. It's also equal to K Q2 Q3 over R squared. What would that give you? 8.99 times 10 raised to power 9 times what's my Q2? What's my Q2? If you check, Q2 is what? Minus 2 times 10 raised to power minus 6. Altogether. But
Yes.
this is an absolute value. Your minus 2 is going to cancel as 2. Altogether.
Yeah.
Times 10 raised to power minus 6. Times Q3 is what? 5 times 10 raised to power minus 6. Then, what do we say? All over. What is the distance between Q2 and Q3?
A.
A. Exactly. Q2 and Q3. A. And my A is 0.1. So I have 0.1 squared. So if you do this, you are going to get 8.99 newtons. Now, we got the first in, we got the maximum of the point. Now, next one is that one. Let us now resolve this force into its component from magnitude and direction. That is resolved into vertical component and also horizontal component. Now, F13. Now, let's go. Look at F13. Now, let us resolve this force to horizontal and also to vertical. Now, check. If I resolve this force to horizontal here, it will be what? It will be what? F13 cos 45 degrees. Are you there?
Yes.
And if I resolve it to the vertical here, it will be what? F13 sine 45 degrees. Observe, they are both positive. They are both going to the positive x-axis. This is going to a positive y-axis. So it means that F13 will be equal to what? Check. F13 cos 45 degrees. Since it's going to the positive x-axis, I'll be having I, positive I with it. Remember, I represent the x component, then J represent the y component. All together?
Yeah.
This is what sine 45 degree J. So if I input everything I have, what would that give me? What's F13? 11.24. So 11.24 cos 45 degrees I plus 11.24 sine 45 degrees J. So F13 in its component order 7.95 I plus 7.95 G. Sine 45 and cos 45 are the same thing. So this is expected to be this. That's for that. Similarly, let us go and resolve F23. Now check. If you observe that F23 is going straight to the x-axis, which means that the component of this is just negative F.
F13. F23 rather.
So 3. Oh, remember, it's going to the negative x-axis.
Yeah. Yes, sir.
It's facing the negative what? Please, I'm coming. Negative x-axis. I'm coming. So, what is now the resolution? What is now the resolution? I'm coming. What's now the resolution? So, it's very easy. You're just going to say, okay, my F23 will be equal to what? Will be equal to negative F23I. It's just going to the negative axis, and that's what? Minus 8.99I.
I.
Altogether.
Yeah.
Therefore, lastly, my F, the force on 3, F3 net, the resultant force is what? The vector sum of these forces. So if I add these two forces together, what do I have? Add this. Remember, we are adding this. We are adding this to this. So add the I to the I. Sorry, I mean, This one, these two is what you're adding together. So add the I to the I and the J. This one does not have J. This one does have 0 J. So if I add them together, I'll be having
minus something.
minus 1.04 I
I
plus 7.95 J. So that's what I have. Then this is what Newtons. That's my final answer in vector form. But if they ask you to find the magnitude, how do we find the magnitude of this? These are our final answer though. But how do we find the magnitude? It's easy. To find the magnitude, you just say F3, the magnitude is just square root of minus 1.04 square plus 7.95 square. Altogether,
yeah.
we'll get the magnitude. But how do we get the direction? That's where everything will twist. Because people always make mistakes. Now, this I always tell students to do. Draw your 4 cardinal points. If you observe the resultant force, you will see that in the resultant force, I have this, like I have negative x axis here, and I have positive y axis. That what the net force is. It means that I'm coming. Please hold on. Can you hear me?
Yeah.
It means that the net force is going to the negative x axis and positive y axis. So pay attention. There's an angle to the x axis here, which is theta. You see this theta? This theta is arctan of y over x, and that's 7.95. Remove this negative 1.04 altogether.
Yeah.
That's arctan of y component over x component altogether. So just do this.
Yeah.
Now, whatever you have, you will get an angle here. You get an angle here. Then, so now you see your angle. We need your angle. We need this angle. I'm coming. This angle that we need there is the angle. Is this angle that this your resultant force makes with the positive x axis? This is angle you need.
Okay, so that's the 180 minus what I get.
Exactly, that's the angle you need. Yeah, that is exactly the angle you need.
Okay.
That's the angle you need exactly.
Okay.
That's the angle you need.
So I can have a question.
What is
very
it?
fast. Can I ask a question in the exam? Because it's too long.
Oh, this is the part that will make you understand it. This type of question is in your slide, something like this. So don't worry, I have some shorter questions. You see, question can be asked right from this first. Everything might not be calculation. That's why I started from something like this. Everything might not be calculation.
Okay.
Quantization of charges, all this stuff. So just understand. So whatever angle you just get here, try to do this in your calculator. Do you have a calculator with you?
Yes. Okay. 7.95 over 1.04, 7.95 by 1.04. So shift down of my answer. So I got 82.55.
What is it?
82.55.
82.55 degrees. So your angle, the angle that is needed is the one that is making the positive x axis. So it will 180 minus 2.55. So what do you have?
97.45.
That 97.45 degree. Now say with the positive x axis.
Okay.
Yeah. So that's how to do it.
Okay, sir.
Okay. So I will print this thing and send the note to you. Any question, please?
No, sir. Understood.
So I'm going to send questions across to you. Okay.
Okay, sir.
All right. So take care. Bye.
Thank you, sir.
Yeah,
Bye,
take
sir.
care. Yeah, bye.